This recording is part 1 of 3 for Chapter 2, The Chemical Level of Organization. Matter is the stuff of the universe. Matter is defined as anything that takes up space and has mass. Mass does not vary with gravity. Weight is what varies with gravity. A person might weigh less in outer space, however, his mass does not change. Matter comes in different forms. There are solid forms of matter, which take on a definite shape and volume. There are liquid forms of matter, where the volume is definite, but the matter will conform to the shape of the container. And finally, gas. Gas does not have a definite shape or volume. Energy is the capacity or ability to do work or to put matter into motion. The more work, the more energy that is used. When you look at this slide, who would you think is using more energy and doing greater work? The man on the left bunting the ball, or the hitter on the right hitting a line drive? There are different kinds of forms of energy. We have what we call potential energy, which you can see on the left. Potential energy is stored energy. The ball has the potential to go down the hill, even though it's not moving. Kinetic energy is energy where things are moving and include inertia. Here we have kinetic energy as demonstrated by the ball actually rolling down the hill. Energy comes in many different forms. Kinetic energy comes in forms including thermal energy, mechanical energy, electrical energy, magnetic energy, sound energy, and light energy. Potential energy, the energy that's stored to be used at a later time, include chemical energy, elastic energy, nuclear energy, and gravitational energy. Atoms are the smallest units of matter. They contain subatomic particles. Protons and neutrons are the subatomic particles found in the center of the atom, referred to as the nucleus. Protons carry a positive charge. Neutrons are neutral. They do not have a charge. Orbiting the nucleus, we can find negatively charged electrons. The electrons orbit the nucleus at various levels, called energy shells. When we look at atoms of different elements, you'll notice the atomic number is equal to the number of protons. The number of protons is also equal to the number of electrons. The atomic mass is defined as the number of protons plus neutrons. The mass is everything in the nucleus. Why doesn't the mass include electrons? If you were to step on a scale and an eyelash were to fall off, the number on the scale would not change. Electrons are very light, and the atomic mass doesn't change with the number of electrons. Elements are the fundamental substances that make up all matter. We've got lots of different elements that you can see some of here on the periodic table of elements. Some examples of elements include things like hydrogen, helium, oxygen, carbon, nitrogen, chlorine, sulfur, phosphorus, barium, aluminum, potassium, xenon. Those are different types of elements. When two or more atoms form a bond, a chemical bond, they make what is known as a molecule. A compound occurs when two or more different atoms are joined together by chemical bonds. If we look at the first example of molecules, you'll see two atoms of oxygen bonded together, making a molecule of oxygen. You also see two atoms of hydrogen bonded together. That makes a molecule of hydrogen. While compounds are also molecules, they're different from molecules in a sense that they have two or more different types of atoms joined together. So even though glucose, methane, and carbon dioxide are compounds, they're also molecules. However, not all molecules are compounds. The major elements of the human body include carbon, oxygen, hydrogen, and nitrogen. If you spell those letters out, C-O-H-N, that might help you remember which are the four most abundant. They're not in order. You don't need to know the order of abundance. Just know carbon, oxygen, hydrogen, and nitrogen are the four most abundant elements in the human body. And of course, you can see other elements listed in this chart. Subatomic particles, which we've already spoken of in a previous slide, are located in the nucleus of an atom and orbiting around the nucleus, depending on which subatomic particles we are viewing. In the nucleus of the atom, we find protons and neutrons. Orbiting around the nucleus, we see electrons. Remember, protons have a positive charge. Neutrons have a neutral charge. They don't carry a positive or negative charge. Electrons have a negative charge. If you look on this slide, you'll notice that protons have a mass of 1 atomic mass unit. Neutrons have a mass of 1 atomic mass unit. Electrons, as I've mentioned earlier, are so tiny that they only have a mass of 1/2000th of an atomic mass unit. Atoms, prior to any kind of chemical reaction, will always have an equal number of protons and electrons. The number of protons and electrons for an element will always be equal prior to a chemical bond forming. However, there are times that the number of neutrons may vary within an element, forming what are known as isotopes. Isotopes with more neutrons than are normally found are referred to as heavy isotopes, which are considered to be unstable and therefore radioactive. Some radioactive isotopes are used in medical imaging. The periodic table gives us an idea of how many protons, and therefore electrons, are found in each element. If we look at the top left, where hydrogen is located, you'll notice that it has the atomic number of 1 because it has 1 proton. If we look at carbon on the right side, over here, you'll notice that carbon has an atomic number of 6. Underneath the word carbon is the atomic mass, which is 12 point something. In order to determine the atomic mass of an element, a sample of that element is taken and the mass determined by the sample, which may contain isotopes. That's why with 6 protons, the average sample of carbon tends to have 1 or 2 more neutrons in the nucleus. Reading the periodic table, the large letter, or large letter and lowercase letter in many cases, is known as the atomic symbol. I'm beginning with that because it's large and stands out. This is the atomic symbol for carbon, merely the letter C. You'll notice a small number to the left and above the letter C, which is the atomic number. The atomic number indicates the number of protons in the nucleus for carbon. The atomic mass, which is sometimes interchangeable with atomic weight, the atomic mass is the average mass of all isotopes in a given element. When we see the number 12.011, again, that indicates that there are probably a few more atoms of carbon that have an extra neutron. Now we're going to delve further into the configuration of the atom. We know that the nucleus contains protons and neutrons. Orbiting the nucleus is where we find the electrons. The electrons orbit in what are known as energy shells or electron orbitals. If we look at the lower diagram, or the lower portion of the diagram, we'll notice that the nucleus is identified by a gray circle, and there are circles around that gray circle in turquoise. This first atom on the left has 2 electrons denoted by those smaller blue circles. If there's 2 electrons in the shell, how many protons would there be? You're right, 2. The first shell of any atom can only hold 2 electrons. If an atom has more protons and therefore more electrons, a second shell will form for those electrons beyond the first 2. The second shell can only hold 8 electrons, as can the third shell. If we had an atom with a third shell, the maximum number of electrons it could hold would be 8. If we look on the far right at the bottom, we see the first shell with 2 electrons and the second shell with 10 electrons. The outermost shell of an atom is referred to as the valence shell. Atoms are stable and unreactive, or inert, when the outermost shell is completely full. Here we have an atom of hydrogen, which has 1 proton and 1 electron. To the right, at the top, we have an atom of helium. Helium has 2 protons and therefore 2 electrons. You'll remember that the first shell can only hold 2 electrons. Therefore, this valence shell is completely full, and helium, one of the noble gases, is referred to as being inert because it is stable and unreactive. On the lower left, we see an atom of carbon with the first 2 electrons in the first shell and 4 electrons in the valence shell. Carbon will want to form a chemical bond with other atoms because it has places where this valence shell could take on more electrons in order for it to be satisfied. On the lower right, we see neon. Neon is another noble gas. It has 2 electrons in the first shell. It has 8 electrons in the second shell. Remember that the second shell can only hold 8 electrons. Because the valence shell for neon is also completely full, neon is also inert and referred to as a noble gas. Atoms that have a positive charge are referred to as cations. Atoms that have a negative charge are referred to as anions. Let's look at these particular substances and find out what they are. Sodium, with that positive charge, is an ion. Oxygen is a molecule. Notice that it's not a compound because it only has one type of atom. Potassium, with its positive next to it, is an ion. Carbon dioxide is both a molecule and a compound. It's a molecule because it contains 2 or more atoms. It's a compound because those atoms are different. Here's a molecule of nitrogen, a molecule and compound of methane, a molecule and compound of glucose. Sodium, as I mentioned before, because it's got a positive charge, is also a cation. Potassium is a cation. Chlorine is an ion, however, it's negatively charged, so it is an anion. We know that atoms that have full valence shells are inert because they're stable and unreactive. Not all atoms have full valence shells. Looking at sodium on the upper left of this picture, we notice that because sodium has 11 protons, there are 11 electrons, 2 in the first shell, 8 in the second shell because the second shell can only hold 8, and the outermost valence shell has 1 lone electron, right here. Chlorine has 17 protons. With chlorine's 17 protons, 2 are in the innermost shell, 8 in the second shell, leaving 7 in the outermost or valence shell. This means that there's room to put another electron here, making chlorine stable with 8 electrons. When sodium and chlorine approximate, get close to one another, what happens is the electron from sodium actually leaves the valence shell to join the valence shell of chlorine. And when that occurs, you'll notice that chlorine on the bottom has a negative sign attached to it because it has gained a negative electron. Technically, sodium on the left should have a positive charge written next to it. I'm going to put a little positive here because sodium lost a negative electron. When negativity is lost, things become more positive. So you have a positively charged sodium ion and a negatively charged chlorine ion. These opposite charges attract sodium and chlorine together. And by the way, when chlorine gains that electron, it's now referred to as chloride. So now we have sodium chloride, which is table salt. This is an ionic bond. Ionic bonds occur when atoms gain or lose electrons. The atom that lost an electron becoming positively charged is now referred to as a cation. Cations have a positive charge. The atom that gained an electron, gaining negativity, is referred to as the anion. Anions have a net negative charge. Ionic bonds form because the cations, which are positively charged, and anions, which are negatively charged, are attracted to one another, and they form ionic bonds. These are very strong bonds. In larger groups, these ions will form crystals called salts. In the previous slide, we saw table salt is formed with an ionic bond, sodium chloride. Water has the ability to break ionic bonds in salts, thereby releasing those charged atoms. What are these charged atoms called, or particles? Electrolytes. Electrolytes are charged ions in water. Electrolytes are important because as they dissociate or come apart in water, they're actually capable of conducting an electrical current. There are many different types of electrolytes that dissociate or come apart in body fluid, including sodium chloride, potassium chloride, calcium phosphate, sodium bicarbonate, magnesium chloride, sodium hydrogen phosphate, and sodium sulfate. When placed in water, the electrolytes you see on the left will dissociate in water, releasing those charged ions that you see on the right. Electrolytes are important for our bodies because they help conduct energy. They also help regulate fluid balance. They're essential in transporting nutrients, supporting proper nerve function, proper muscle function, because they support nerve function, obviously mental function. Our nervous system is made up of nerves, including our brain. Electrolytes can also help convert calories into energy. They regulate our pH throughout our body, which varies in different areas of the body. And there's many, many other roles of electrolytes. Another type of chemical bond that can form is a covalent bond. Covalent, valent, meaning valent shell, means that our electrons are being shared in the outermost shell of the atom with another atom. There are two types of covalent bonds. These types are dependent upon whether or not polarity is established. What's polarity? If you've ever used a magnet, you'll know that it has a north pole and a south pole. Or if you've ever put a battery into a device, you'll notice that there's a positive end and a negative end. That's polarity. There's a net charge between the ends. With a nonpolar covalent bond, the electrons are shared equally in the valence shells of the atoms involved, and there is no net charge formed in this type of bond. The positive protons are pulling at the electrons equally, and so a good analogy would be if you have a best friend and the two of you played in each other's backyards for equal amounts of time. That would be a good analogy for a nonpolar covalent bond. Nonpolar molecules have some distinct properties. They are fat soluble, they do not dissolve in water, they diffuse or travel easily through cell membranes, and all compounds with only carbon and hydrogen, and those with identical atoms, such as a molecule of hydrogen, are nonpolar. Common nonpolar covalent molecules include carbon dioxide, oxygen, fats, and some amino acids. Amino acids are the building blocks of proteins. Now think about this for just a second. Carbon dioxide and oxygen pass through cell membranes easily. This is important for our bodies. Here are more examples of covalent bonds. Here are two hydrogen atoms equally sharing their one electron. That fills their valence shell with 2 electrons. Here we have carbon forming a covalent bond with oxygen on one side and again on the opposite side. Nonpolar covalent molecules tend to be linear, so they form a line. Here's that linear configuration. When an atom shares one electron with another atom, that's referred to as a single covalent bond and is denoted by a single line between the two letters that denote that atom. You'll notice that carbon on the next picture is sharing 2 electrons on each side with the oxygen on either side. This sharing, because it involves 2 bonds between carbon and oxygen on one side, forms a double bond here, and on the other side we have the same thing, a double bond between carbon and oxygen. The double bond is denoted with 2 lines, so you have oxygen double bonded with carbon, which is double bonded with another oxygen, and that is carbon dioxide. On the bottom left, we have 2 oxygen atoms bonded together, forming a molecule of oxygen. And on the lower right, we see that we have a triple bond formed between an atom of nitrogen and another atom of nitrogen, forming a molecule of nitrogen. And we can see the triple bond is denoted by 3 lines. Again, nonpolar covalent bonds are where electrons are shared equally. Since the body is made up of mostly water, and nonpolar compounds are fat-soluble. They don't mix well with water. We need to have a way to transport these nonpolar compounds through different types of watery mediums, such as blood in the bloodstream. If you look at the picture on the left-hand side, you'll see a lipoprotein. The lipoprotein has an outer capsule made up of molecules that have polarity on the outer surface. So we have phospholipids, which have a polar head on the outside, and embedded proteins, like apoproteins, on the outside of the capsule to transport the triglycerides inside. Low-density lipoprotein and high-density lipoprotein are two examples of lipoprotein structures that will help transport fat through the bloodstream. If you look to the picture on the right, you'll see a picture of hemoglobin. Hemoglobin is a protein, and most proteins are polar. With hemoglobin, we can transport nonpolar carbon dioxide and nonpolar oxygen on the hemoglobin protein throughout the bloodstream. Polar covalent bonds include sharing. However, because there is polarity, the sharing of electrons is not equal. The analogy for this would be, instead of spending equal time in your best friend's backyard, if you insisted that that person play in your backyard longer, then there's unequal sharing. If we look at the water molecule on the top right of this slide, you'll notice that oxygen has a partial negativity, and the two hydrogen atoms have partial positivity. You'll also notice that this molecule is not linear. It's got a bent configuration or shape. Why does this happen? Well, oxygen has an atomic number of 8. That means it has 2 electrons in its innermost shell and 6 electrons in its valence shell. With 6 electrons in its valence shell, it would require 2 more electrons to be happy. So I'm just going to draw the outer shell. Pretend the inner shell is already drawn. Now, hydrogen only has 1 electron, so it can share its 1 electron, and then this hydrogen is going to share its 1 electron. We already have 6 electrons in the outermost shell. That means if we add 2 electrons, that fills up that valence shell for oxygen, and the 8 protons in the nucleus of oxygen are going to draw the electrons of hydrogen in towards oxygen for longer periods of time. So even though there are electrons from oxygen being shared with hydrogen some of the time, so 1 electron from oxygen will play in the backyard with hydrogen, and 1 will play over here, the electrons tend to spend more time in oxygen's backyard. That causes the molecule to bend, and that is what creates a partial negative charge for oxygen and a partial positive charge for hydrogen. The electrons are not completely given up. That's why there's not a negative gain of +1 or -1, but just that partial negativity, partial positivity, respectively. Certain molecules tend to create polar covalent molecules. Water's the biggest example of polar covalent molecules that we have in our body. Sugar is a polar covalent molecule. There are certain amino acids. Most proteins have the property of being polar covalent molecules. Polar covalent bonds will dissolve in water, and they do not freely diffuse through the cell membrane. Remember that oxygen and carbon dioxide will, but polar covalent molecules will not. Here we have an actual diagram of an oxygen atom, and you can see the 8 protons, 8 neutrons in the nucleus. You can see 2 electrons in the innermost shell because it can only hold 2 electrons. And then we see that 8 minus 2 would leave 6 electrons. So there are 6 electrons that belong to oxygen. However, it's going to share an electron with a hydrogen atom on one side, and it will share an electron with a hydrogen atom on the other side, while the hydrogen atoms share their electrons with the outermost shell of oxygen. Again, the electrons are pulled toward the positive nucleus of oxygen more often than they are hydrogen, because hydrogen only has a net positive charge of 1. There is only 1 positive proton in this nucleus. So there's more pulling power from the oxygen atom than there is from the hydrogen atoms. Like dissolves like. Water, having polar properties, will dissociate or pull apart ionic compounds. It will also dissociate polar covalent bonds. So the bonds found in sugar and some amino acids, most proteins. Like dissolves like. Because of the polarity of water, it can easily affect and dissociate ionic bonds as well as polar covalent bonds. So again, sugar, some amino acids, proteins, most proteins, not all, but most. Water does not dissolve nonpolar covalent compounds, so it will not dissolve carbon dioxide, oxygen. Fats have a lot of carbon-hydrogen bonds. Some amino acids are fat soluble, but that's pretty much it. This concludes part 1 for chapter 2. I'm going to go ahead and record the next portion.